NEC 430.24 is applicable for sizing a feeder that exclusively supplies motors. Applying this to a scenario, the feeder conductors can be sized at 125% times 124 plus 124 plus 77 plus 11, equaling 367 amps, based on NEC 430.24. Now, NEC 215.2 stipulates that feeder conductors must be sized at 125% of the continuous load added to 100% of the non-continuous load. Here, the continuous load is the combined motor nameplate amperes, which is 124 plus 77 plus 11, totaling 212 amps. Presuming there's no non-continuous load, the feeder conductors would necessitate a sizing of 125% times 212 amps, which comes out to 265 amps. Given that the feeder conductors are rated at 400 amps, either method is viable for sizing the conductors. However, opting for the NEC 430.24 method generally proves more cost-effective, as it leads to a smaller conductor size. Now let's discuss continuous and non-continuous loads in more detail. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Examples of continuous loads include lighting in a commercial building and heating and cooling systems. Non-continuous loads are loads where the maximum current is not expected to continue for 3 hours or more. Examples of non-continuous loads include receptacles and small appliances. When sizing feeder conductors, it is important to consider both continuous and non-continuous loads. Continuous loads must be increased by 25% to account for the fact that they will be operating for an extended period of time. Non-continuous loads do not need to be increased by 25% because they are not expected to operate for an extended period of time. The general process for sizing feeder conductors for motor loads under the National Electrical Code involves several steps. Firstly, determine the full load current, or floor, for each motor from NEC tables 430.247, 430.248, 430.249, and 430.250. These tables provide the FLA based on horsepower, voltage, and motor type. Secondly, calculate the ampacity of the feeder conductors. According to NEC 430.24, the feeder conductor ampacity must be at least 125% of the largest motor's FLA, plus the sum of the FLA of all other motors in the group. Thirdly, select the appropriate conductor size based on the calculated ampacity and the conductor's insulation type and temperature rating, referring to NEC Table 310.16 or other relevant tables. Fourthly, calculate the minimum size of the grounding electrode conductor, or GEC, for the feeder, based on the size of the feeder conductors, as specified in NEC 250.66. Fifthly, size the feeder overcurrent protection device, or OCT, such as a circuit breaker or fuses. The OCT must protect the feeder conductors against overcurrent and short circuits, and its rating should not exceed the conductor's ampacity, as per NEC 240.4. Now let's consider motor contribution to fault current. When a fault occurs in a motor circuit, the motor itself can contribute current to the fault. This contribution needs to be considered when selecting and coordinating overcurrent protection devices. Motors act as generators during a fault, feeding current back into the system. The amount of fault current contributed by a motor depends on its size, impedance, and speed. Typically, motor contribution is estimated to be several times the motor's full load current. This fault current contribution needs to be accounted for when performing short circuit studies to ensure that the overcurrent protection devices can interrupt the fault current safely and effectively. Coordination of overcurrent protection devices involves selecting and setting the devices so that they operate in a specific sequence during a fault. The goal is to isolate the fault as quickly as possible while minimizing disruption to the rest of the electrical system. In a motor circuit, the overcurrent protection devices must be coordinated to allow the motor starting current to pass without nuisance tripping, but still provide protection against overloads and short circuits. The selection of overcurrent protection devices for motor circuits can be complex, and it is important to consult the NEC and other relevant standards. Short-circuit studies are used to determine the magnitude of fault currents at various points in an electrical system. These studies are important for selecting and coordinating overcurrent protection devices. Short-circuit studies are typically performed using computer software that simulates the electrical system and calculates the fault currents. The results of the short-circuit study can be used to determine the appropriate ratings and settings for the overcurrent protection devices. Let's consider an example. Imagine a feeder supplies 3 motors. Motor 1 has a full load current of 40 amps, Motor 2 has a full load current of 30 amps, and Motor 3 has a full load current of 20 amps. According to NEC 430.24, the minimum ampacity of the feeder conductors would be 125% of the largest motor's FLA, which is 40 amps, plus the sum of the FLA of the other motors, which is 30 amps plus 20 amps. So, the calculation would be 1.25 times 40 plus 30 plus 20, which equals 50 plus 30 plus 20, totaling 100 amps. Therefore, the feeder conductors must have an ampacity of at least 100 amps. Now let's talk about motor protection. Motor protection is addressed in NEC Article 430, which provides detailed requirements for protecting motors, motor circuits, and motor control equipment from overloads, short circuits, and ground faults. Proper motor protection is essential to prevent motor failure, equipment damage, and potential safety hazards. Overload protection is designed to protect the motor from damage due to excessive current draw over an extended period. Overloads can occur due to various factors, such as mechanical overload, voltage imbalance, or winding insulation degradation. NEC 430.32 and 430.34 specify the requirements for overload protection, including the selection of overload relays, thermal protectors, or other devices that will trip the motor circuit when an overload condition is detected. Short-circuit protection is designed to protect the motor and the motor circuit from high fault currents that can occur during a short circuit. Short circuits can be caused by insulation failure, accidental contact with grounded surfaces, or other factors. NEC 430.51 through 430.58 provide the requirements for short-circuit protection, including the selection of fuses, circuit breakers, or other devices that will quickly interrupt the fault current and prevent damage to the motor and the circuit components. Ground fault protection is designed to protect personnel from electrical shock hazards that can occur when a ground fault exists in the motor circuit. A ground fault occurs when a live conductor comes into contact with a grounded surface such as the motor frame or the equipment enclosure. NEC 430.51 and 430.53 provide the requirements for ground fault protection, including the use of ground fault circuit interrupters, or GFCIs, or other devices that will detect the ground fault and trip the motor circuit. Moreover, consider the effect of harmonics on motor feeders. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental frequency, typically 60 Hz in the United States. Harmonics can be generated by nonlinear loads such as variable frequency drives, electronic ballasts, and uninterruptible power supplies. Harmonics can cause a variety of problems in electrical systems, including overheating of conductors and transformers, increased losses, and misoperation of equipment. In motor circuits, harmonics can cause the motor to overheat, vibrate, and experience reduced lifespan. Harmonics can also cause the motor protection devices to misoperate, leading to nuisance tripping or failure to protect the motor from overloads or short circuits. To mitigate the effects of harmonics in motor circuits, it is important to use harmonic filters, reactors, or other devices that can reduce the harmonic content in the electrical system. It is also important to properly size the motor feeders and overcurrent protection devices to account for the increased current and heating caused by harmonics. Next, let's address voltage drop considerations for motor feeders. Voltage drop is the reduction in voltage that occurs along a conductor due to the impedance of the conductor and the current flowing through it. Excessive voltage drop can cause a variety of problems in motor circuits, including reduced motor torque, decreased motor speed, and increased motor heating. NEC 410.19 AON and 215.2 ATHV provide guidelines for minimizing voltage drop in branch circuits and feeders. These sections recommend limiting the voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop in motor feeders, it is important to select conductors with adequate ampacity and low impedance. It is also important to keep the feeder length as short as possible and to avoid unnecessary bends or connections. Another important factor is the ambient temperature. The ambient temperature is the temperature of the air surrounding the conductors. The ampacity of a conductor is based on the assumption that the ambient temperature is within a certain range, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than this range, the ampacity of the conductor must be derated to account for the increased heating. NEC Table 310.15b2 provides the derating factors for conductors at various ambient temperatures. Another consideration is the number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in the same raceway or cable, the ampacity of each conductor must be derated to account for the increased heating. NEC Table 310.15b3 provides the derating factors for conductors in raceways or cables with various numbers of current-carrying conductors. Regarding conductor types and insulation, there are various types of conductors and insulation materials available for use in motor feeders. The selection of the appropriate conductor type and insulation material depends on the application, the ambient temperature, the voltage, and the environmental conditions. Common conductor types include copper, aluminum, and copper-clad aluminum. Copper conductors have higher conductivity and lower resistance than aluminum conductors, but they are also more expensive. Aluminum conductors are lighter and less expensive than copper conductors, but they have lower conductivity and higher resistance. Common insulation materials include thermoplastic, thermoset, and rubber. Thermoplastic insulation is less expensive and easier to work with than thermoset insulation, but it has lower temperature rating and less resistance to moisture and chemicals. Thermoset insulation has higher temperature rating and better resistance to moisture and chemicals than thermoplastic insulation, but it is more expensive and more difficult to work with. Motor starting methods can also affect feeder sizing. The method used to start a motor can have a significant impact on the current drawn from the feeder. Some motor starting methods, such as across-the-line starting, can draw a very high inrush current, which can cause voltage drop and stress on the feeder conductors and overcurrent protection devices. Other motor starting methods, such as reduced voltage starting, can reduce the inrush current and minimize the impact on the feeder. Common motor starting methods include across-the-line starting, reduced voltage starting, and soft starting. Across-the-line starting is the simplest and most common motor starting method. In this method, the motor is connected directly to the power supply, and the motor draws a very high inrush current during starting. Reduced voltage starting methods use various techniques to reduce the voltage applied to the motor during starting, which reduces the inrush current. Common reduced voltage starting methods include autotransformer starting, reactor starting, and part winding starting. Soft starting methods use electronic devices to gradually increase the voltage applied to the motor during starting, which minimizes the inrush current and provides smooth acceleration. Soft starters can also provide additional features, such as overload protection, undervoltage protection, and phase loss protection. The NEC provides guidelines and requirements for motor feeders to ensure safety and proper operation. Adhering to these codes is crucial for electrical installations.